Hello everybody, welcome to the Tech Talk series for Google Waterloo. Today's speaker is Pascal Poupart. He is an assistant professor at University of Waterloo, and he has also received 2 Google Research Awards, which makes his research quite interesting for Google. And today he will talk about active learning and a reinforcement learning approach. So, Pascal?
Okay. Well, thank you very much. The topic is non-myopic active learning, a reinforcement learning approach. And I guess I should say at the outset that this will be a fairly theoretical talk. So I know Google, a lot of people care about scalability and so on, but then I guess you need to have the data to worry about these problems. So this is work that I've done in the past few years, but mostly from a theoretical perspective. But the idea is that if you understand well the theory, then perhaps it'll help you in designing practical algorithms as well. So that's the philosophy, that I use when I do research, and hopefully, everybody can appreciate it from that perspective too. Okay, so here's the outline. We'll go over some of the basics for active learning. Then I'll talk about Bayesian reinforcement learning and how we can use it for the non-myopic version of active learning. Then I'll talk about, if we frame this as Bayesian reinforcement learning, how we would come up with a good strategy, and that'll mean coming up with a parameterization for the value function, and then an algorithm called BEETLE, and then a few experiments. Okay, so what is active learning? So let's start with supervised machine learning. So I'm sure that for a lot of you that won't be anything new, but let's just make sure we've got the basics in place. So let's say we've got some data, x and y, where x is going to be our input. It can be, of any dimensionality, it doesn't matter. And then y, just for the sake of, this talk, is going to be something binary, either plus or minus. And then, so let's say we've got a data set right here. Okay, and then the question for supervised learning is how can we come up with perhaps a separator that would identify, I guess, those 2 classes, and as well as any other point that's not already part of our data set, right? So that's a classic supervised machine learning problem. Now, in many situations, though, what happens is that we start with just data that's not labeled, so we don't know what the classes are, right? And then we still want to do classification, but we have the option of requesting the labels. Okay, so in that situation, then we could ask somebody, let's say for the sake of this talk, we're just going to call this person an oracle, to tell us what is the answer for some of those points, and we just submit those points. Okay, so perhaps I just submitted a point, it returned and came up as a plus here. Then I could ask for another point, maybe this one there, and it's a minus. And we keep on going like this. We keep on requesting some points. So we convert them into labeled data, and then eventually we'll have enough information perhaps, and then we can classify the data. Okay. So, but then the question with this is, what's the best way of, I guess, requesting the data? What points should we ask the oracle to label, right? Because you can see that I just drew the line somewhere that kind of makes sense based on those 4 points, but I could have drawn it elsewhere, and maybe some other points could have been more informative, right? Okay, so that's the main question. How do we choose the data to be labeled? Okay, so there's some basic ideas out there, and I mean active learning is not a new problem, and perhaps the most popular approach is what is known as a greedy approach. Okay, so basically, you simply go for the point that will give you the most information. And let's say that we're in a situation where we're coming up with linear classifiers like this. And let's say I've only got those 4 points that are labeled. Then the points that would make sense to label after that would be those that I put in dark blue, because they're still uncertain, right? The other points, the green ones, if I go with the assumption that my data is going to be linearly separable, right? You could assume that these guys are going to be pluses and these guys are going to be minuses, right? So the only real uncertainty is with respect to the blue ones, and then we just need to ask ourselves perhaps, which point is going to give us the most information, and then go for that point, right? Now, ideally, if we really want to be optimal, it would be nice as well to consider, I guess, an entire sequence of queries and then see perhaps which sequence is really the best one. For a simple setting like this, often greedy does well, but ideally if we truly want to be optimal, that's what we should do. Now we're going to see some other settings where actually going for an optimal sequence will actually be more important, and this will lead to non-myopic active learning. So when you're greedy, you're essentially being myopic, right? And when you're going for the optimal sequence, then you're trying to not be myopic. Okay, so let's go as well through some examples just to make things concrete. And I wasn't quite sure which example to pick, and then since I'm here at Google, I picked two that should make sense to people here, but then I know there's also a danger that you guys know so well those examples that I hope I won't say anything wrong here, but we'll keep those examples simple anyway. Okay, so document classification, classic problem, where you've got some data that's a corpus of documents, and then so that means for each document we want to come up with the topic that it should be part of, and then let's say we've got a classifier, let's say just a naive Bayes model. So then a greedy active learning approach could simply estimate what is the topic distribution for each document, and then based on that we could simply request the label of the document that is the most uncertain. Okay, so this would be a simple greedy active learning approach. Assuming that we've got a classifier like a naive Bayes model that gives us a distribution over the possible classes. Right? So if we've got that, then we know how certain we may be or not certain, and then we can refine, I guess, our estimate, our classifier, by always picking the document or the point that we're the most uncertain about. Okay. All right. Now let's look at something more interesting. Budgeted learning. So in many cases, the data that you would have to get it labeled doesn't come for free. Okay, so so here you could think of your data as coming up with, like, each point could be have a cost assigned to it, and then when you request a point, then you'll pay the price for that point, and then simply get the label, right? So again, we could go, say, for the cheap ones, and then perhaps they're going to give us plenty of information, but in some cases, maybe the more expensive ones will give us more information. So it's not always clear which ones to pick, right? By the end of the day, at some point, we're going to have a classification again, and it's really just a question here of maximizing, I guess, the value of information. And again, we could be greedy, but in some cases as well, it'll make sense to go for something that's non-myopic, that is over a long period of time. Okay, so in the context of document classification, this would be an example where, say, we've got a budget where, let's say we've got a research assistant, maybe a linguist, who's just going to read documents for one day and then label them. But then the problem is that if the documents are long, right, then it will take longer. So it would be better if we just submitted to, you know, the linguist shorter documents so that he or she could label more of them, right? So in this case, you see, just going for the documents that are the cheapest may not yield the best strategy, or those that are the most informative in the sense of reducing the uncertainty the most, that may not be the best strategy either. So you really want to look at, I guess, the value of information. Okay, and then so that's our dilemma here. So do we go for shortest unlabeled document or document with the most uncertain topic? Okay, now here we can add one more twist to this, where you could say that in many situations the oracle is not perfect, so perhaps the person won't label a document per se, but simply tell you how good is your guess about the topic or the label of some document. So here in this setting, right, we're going to have some data again, but we don't. When we request, what we submit to the oracle is not just a point for which we're going to get the label, but instead we submit a point with our guess of the label, and then we get a reinforcement just some kind of score that tells us how good that label would be. Because in some situations, all labels are kind of okay, just that some of them are better than others. Okay. So it would lead to this setting where, again, we've got our inputs, we don't know the label, but now the cost is a function from every input label pair, right? And that cost essentially just tells us how good that label was. And perhaps this could be noisy as well. Okay? And then here we simply want to come up with a policy that would map every input to a label, but then we don't get to have like the full, I guess the correct answer from the oracle. So here this could correspond to add placements. And I know some of you guys are working on this and know a lot more than me on this, so I'm sure I'm going to say things that are not quite the way it works at Google, but I thought I'd come up with a simple example. So this is really, a simplified scenario of add placements. Okay? So let's assume that we've got a set of keywords. This is our data, right? And then we need to decide what ads we're going to show. So that's our labels, and then you can think of each keyword as having potential labels that are the ads, and we simply want to get the best one, the one that will perhaps give us the best payoff. Okay. So then in this scenario, what we would really like to know is what the click-through rate is, and then our dilemma is always, well, should we show an ad that has the best expected return so far, or do we simply show an ad that has the most uncertain click-through rate so that we can learn about it, right? And then so you can think of this as like trying to, I guess, maximize immediate profits, right? Where this is more like long-term exploration so that you could maximize your profits down the road because you would know better what is the click-through rate of different ads. Okay? Okay, so we could make this even more complicated, okay, and then you could see all of these scenarios that I've explained as really just being special cases of reinforcement learning. So in reinforcement learning, the added complication is that you really only have, well, you don't get to pick the points that you submit to the oracle. It's more like when you submit something with a label, that will actually influence what is the next point that you're going to get. Okay, so the next data point is influenced by the label. So you're kind of constrained in, I guess, what will be your future choices. So in situations like this, you really need to have a strategy that's non-myopic, because if you only try to, I guess, maximize expected return for, I guess, your immediate label, then you're disregarding what could happen in the future, and maybe the future, right, the possibilities are not going to be as great. Okay? So for situations like this, then you really cannot be myopic. Okay? And then so to model this, right, the added piece is here, where we've got a transition probability that says if we are looking at a specific point, we've submitted a label y to the oracle, then we got a value for it. But on top of that, the next point we will end up in, we don't get to pick it. It will be decided by some transition probability. Okay? And so that's why in situations like this, whenever you've got like this coupling from points that you visit, then being myopic is going to be an issue. Okay, so this would correspond to situations where you've got ad placement with budgets. And again, I'm not going to claim that this matches what really happens at Google, but it's a simplified example where here, let's say that advertisers have budgets. And the idea is that if you keep on displaying the ad of one advertiser, at some point, once the ad has been clicked on enough, perhaps the entire budget will be depleted, and then you won't be able to show it again, right? So that essentially constrains what is your space of I guess, next points. Okay. So here you can think of this as having data that's the set of keywords and a budget for each ad, right? So before we simply had data that was a set of keywords, but now we're going to augment this with the budget, okay, for each ad. And the next point you're going to visit, you can definitely select. Well, I guess the keyword is not decided by you. I mean, it's whoever, you know, submits a query, I guess, on Google's search engine, right? And then for the budget, well, that decreases with each click through, or yeah, with each click. So that's why, in a sense, the points that you get to observe data about, right, are constrained. So you don't get to pick them all the time. So there's this transition probability of going from one keyword with budget to the next keyword with budget, and so on. Okay, the labels are, again, ads. And then again, the goal is the same, but with the condition that we want to satisfy our budgets. Okay. So the problem is the same as before. Unknown click-through rate. We've got the same dilemma, but with the added complication that an ad cannot be shown when the budget runs out. Okay. So this is one example here where perhaps I guess not being like you really don't want to be myopic, or at least not when the budget is about to run out. Maybe at the beginning it's okay, but not near the end. Right? Okay. Does that make sense to everybody? Okay. All right. So now I don't work on ad placement. So what really motivated my research is actually this problem. So what's the connection? Here, we're developing assistive technologies where there's a video camera that monitors what a person is doing at the sink in a bathroom. And the idea is that people with Alzheimer's disease or other forms of dementia have trouble just carrying out simple tasks of daily living like hand washing. So hand washing is nothing complicated for you and I, simply because we're just fine cognitively. But there's actually a sequence of steps where you need to first turn on the water, wet your hands, put soap on your hands, then rinse, and then turn off the water, and then dry your hands. And some of those steps can be interchanged, but otherwise there is an actual sequence. And then the last thing you want is perhaps the person to, I don't know, skip a step like rinsing and therefore just go to dry the hands that are still full of soap, right? And then so a person that has dementia in a hospital will often need to be accompanied, and then a nurse will have to essentially guide the person through those steps. So then the idea here is, can we build a system that will monitor what the person is doing and then give a prompt at every step if necessary to guide the person? And then so here you can think of having data that's the various states of the user. Okay, and these states could involve, like, what step is the person at, and then what's the status of the hands? Are they full of soap? Are they wet? Are they dry? Where's the towel? That sort of thing. And then the label is a prompt. So given a situation, should we give a prompt or not? That's the first question. And then the second question is, should we give a prompt for a specific step, and then how detailed should that prompt be? Okay, so that's our space of labels, and then the goal is to come up with the best prompt for each of those states. That's our policy. Okay, and you can think of this as an active learning problem, again, because the user is unknown. So if we already had, I guess, some information about how the user would react to different prompts, then you could hard code a policy. Maybe like if you've got a grandparent that you know well enough, then you would know like what step your grandpa or grandma is likely to do well and what steps needs to be prompted and so on. But if it's a new person, like let's say it's in a hospital, and this system has to interact with many patients, and then so each person will behave differently, and so you need to learn, I guess, this information, right? So the system here ideally should just try to give the best prompt, but on the other hand, you'd like the system to also learn about the person, Right? So in some cases, the system may decide to give a prompt just so to see how the person is going to react, even though the system knows that this is not likely to be the best prompt. Okay? So we've got, again, this dilemma of exploration and exploitation. Okay? So in any case, that was the research that was motivating, I guess, this work that I'm going to present on Bayesian reinforcement learning. And then this particular system of hand washing has been deployed in a few hospitals, including in Toronto, and I believe there's probably one. Well, actually, yeah. So Sunnybrook was a hospital in Toronto where it was first tested, and then Alex Mihalidis in Toronto is the one who's leading the project for that, and they've developed a few prototypes that are in a few hospitals. Okay. Okay, so reinforcement learning, the big question again is exploration exploitation, and then so that leads to the following difficulties where in contrast to, I guess, other tasks from machine learning, we don't know what is the label for any given point. All we get is a reinforcement, and then we cannot select the data directly either. So it's really like some kind of constrained active learning problem that's noisy because we don't get to have the label, right? We just get to have a reinforcement. And so for these types of problems, then solutions tend to be complicated, and you usually don't want to just have something that's myopic. Okay, so let me now go over some of the basics of reinforcement learning, and then I'll propose an algorithm that can tackle this and can be used for active learning in general, and will be interesting, I guess, for active learning where a myopic solution would not be good. Okay. All right, so reinforcement learning, we can think of it just in this framework where you've got an agent, that's your system. It can perform some actions that will influence the environment, and then it will sense what the effect of those actions are through some observation. And then here I'm going to assume that these observations are fully observable, so I get to see the actual state of the environment. So we could make that even more complicated with partial observability, but for the sake of this talk, we'll just stick with full observability. And then with that, we'll get as well a reinforcement, a reward that will tell us how good the action was just for that time step. And then the agent has a goal or some objective, and it will essentially mean that it tries to maximize those rewards. So that's usually how reinforcement learning is framed, but I mean, active learning can just be seen as a special case here. Okay. Now, more precisely, our formal model comes from Markov decision processes. So we've got a set of states. These are what I called before the inputs. We've got a set of actions. These are what I used to call the labels. And then a transition function that tells us what is the next state that I could reach after executing a certain action in a given state. And then a reward function that's kind of like, if you want, the opposite of a cost that we talked about before for labeling data. Okay. Now, if we're looking at reinforcement learning, not Markov decision processes, the difference is that we don't have this transition function. All we have is a state space, action space, and depending on the problem, you may also have the reward function. So here I'm going to assume that I've got the reward function, but we could also remove that. Okay. So this really corresponds to, I guess, the same as those problems we saw before, where if we don't know, I guess, what is the next point that we could be reaching as a result of labeling the current point, then it would mean that we don't know what is that transition function. And then you'll notice here that we don't know what is the mapping from states to action. So it's the same as before. We don't know which label goes with which data point. Okay, so this is a formal model, and to come up with a policy here, we'll want to maximize expected total reward. So that's one way to set up an objective, and that simply means we're going to maximize the sum of all the rewards that are earned at every time step. Essentially maximizing, I guess, the expected returns of all the ads, that we're placing. Okay, and then so a policy formulae is going to be a mapping from states to actions, or if you prefer, from inputs to labels. And then we're going to look for an optimal policy, meaning a policy that has higher value at every possible state and beats every other policy. Okay. And there are some theorems that says that there's always one that's better than all the others, okay, for every possible state. So we're just going to aim for that policy. All right, so reinforcement learning algorithms come in different flavors. So there's a large body of literature out there, but very often it's divided in two groups, model-free as well as model-based. And what that means is that either you try to learn the part of the model that you're missing. So if you remember, we define reinforcement learning as a Markov decision process where we don't know what the transition function is. So if in our learning we try to estimate what that transition function is, then we're doing model-based reinforcement learning. If we don't try to build that directly and we simply try to come up with a policy, then we're doing model-free reinforcement learning. And so classic algorithms for this, there's Q-learning, TD Lambda, Pegasus, neurodynamic programming. These are all model-free, and traditionally this was the most popular class. In the model-based camp, what's actually quite popular these days are Bayesian approaches. And the idea is that we're going to put a distribution over the unknowns and learn that distribution. Now, if we look at the implications of doing model-free versus model-based, model-free tends to be much simpler because we don't model anything, whereas model-based is actually quite harder. However, in this case here, if you don't model, I guess, your unknowns, then it'll be much harder to come up with a strategy that's non-myopic and that trades off exploration and exploitation. Okay? Whereas in this case, we'll have explicit information about what we know and what we don't know about our model, and then it'll be much easier to have a policy that does properly optimize this exploration-exploitation trade-off. Okay? So, given these differences, I'm not going to focus on Bayesian reinforcement learning because I want to have something that's non-myopic and perhaps does the best in the long term. So therefore, I'll want to optimize my exploration-exploitation trade-off. And we'll show that in the case of Bayesian reinforcement learning, with the right, under the right assumptions, we can come up with an optimal policy. Okay, so we are able to optimize that trade-off. Now, what's really interesting is actually Bayesian reinforcement learning is not new. Okay, so what people usually remember is Q-learning and then all these other algorithms that I put here. And in the literature, these started like in the 1980s, right? And if you read about Sutton and Bartow's book, right, that's essentially the main focus. But it turns out that in the operations research literature, people were already doing reinforcement learning. It wasn't called reinforcement learning, but they were doing it. And it was really what is known today as Bayesian reinforcement learning. So back in those days, it was called dual control, or they had different names. Okay. But in any case, you can look at the papers by Ron Howard and some of his students in the 1960s, and it's quite elegant. Okay, so how does Bayesian reinforcement learning work? The idea is that we've got some unknowns. Here it's our distribution over the next state, given the current state in action. And Bayesian learning simply says, well, let's treat that as a variable and then learn a distribution over that. And that distribution will encode how certain or uncertain we are about that unknown. So here, because what we don't know is a distribution itself, it means these variables are going to be numbers between 0 and 1. And then, I guess, a bunch of those numbers that must sum up to 1 is an unknown multinode unknown multinomial distribution, and then we'll have a prior distribution over these variables, and then the key will be to come up with a posterior that will simply incorporate the evidence we get. So at every step when we execute an action and see the next state, right, then that's additional information that we can use to refine our distribution. Just like, I guess, with ad placement, each time that you display an ad and then you get to observe whether it was clicked or not, that's additional information that you can use to refine your, I guess, belief about what is the click-through rate of that ad. Right? Okay. So what I'm going to do next is show you how we can set up a prior and then refine it to come up with a posterior distribution based on the evidence. Once we've got that explained properly, then we'll see how we can use this as the input to our policy and then have a mapping that will tell us what action we should pick given distributions like this. Okay, so starting with a prior, computing the posterior is also known as belief monitoring. So we've got a belief about our unknown model, and then we compute a posterior simply using Bayes' theorem. So we simply multiply the prior by the likelihood and renormalize. And in this particular setting, what's really interesting is that the math is actually quite simple, because if we're working with a discrete model, right, if our distributions that are unknown are multinomials, then you'll notice here that P of S prime given S, A, and theta is really theta itself. Right? That's our unknown. So what it means is that I've got a prior distribution that I simply multiply by theta. And now the interesting question is there a class of distributions that I could use, multiply by theta, and get a posterior that's in the same class again? So this is known as what are conjugate priors. And for these multinomial distributions, it turns out that Dirichlets work well. And so Dirichlets, okay, if you're not familiar with these distributions, or the name, is a little intimidating, just think of them as multinomials. Okay, so their definition is that you take the product of theta, theta for every unknown probability, okay, every unknown number between 0 and 1, raised to some exponent. So this is really just a multinomial, and why this works well is because if you multiply a multinomial by theta, then you get simply, again, a multinomial where one of the exponents will be raised by 1. Okay? So this is very simple and quite elegant. But then the next question is, well, how do we start? Like, we have to have a prior, and what should be that distribution? So it turns out that there's a nice interpretation for these distributions, where here I've drawn 3 of them. And the idea is that these distributions, they have hyperparameters n that are known as hypercounts. So the idea is that you can think of those hypercounts as like some virtual data that you could have observed before and have led you to set up your prior distribution in the following way. And then so it would be essentially how many times you've seen each theta I event, and then if you take the relative frequency counts, this should kind of give you the mean. So the distribution will have its peak right at the relative frequency counts, and then the height of the peak will depend on how much data like this you could have observed before. Okay, so if you've got the number of virtual counts that's high, then it would mean that it's as if you had already seen a lot of data, and therefore you should be more certain, and therefore this distribution should be more peaked. Right? If you haven't seen that much data, then you would think that the distribution should be more flat, and perhaps if you haven't seen anything, it should just be uniform. Right? So that's the intuition here. So I guess here you see if we set n1 and n2 to be 0.2 and 0.8 times k, where I vary k, all that will happen is that I will simply make my distribution more or less peaked, and then it will have the peak near 0.2, which corresponds, I guess, to the relative frequency counts here. Okay. Does this make sense? Yeah? Okay. All right. So now we have some ideas about how to set those distributions. Then we can compute the posterior by belief monitoring. And so we just apply a Bayes theorem like this, and what it shows is that you multiply the power by theta. That raises one of the exponent by 1, and then you get back a Dirichlet distribution. Okay? And then so the key here is that this is really simple because the computation just means that we're incrementing one of the hypercounts. All right, so now we know how to do monitoring, so we can learn, I guess, the unknown parts of our model very simply. The next question is, how do we act optimally with respect to this information? So we're going to define a policy, but now instead of defining the policy just with respect to the current state, we're going to also define it with respect to our belief about the model, because that's information as well that tells us, what part of the model is well known, what part is not so well known, and perhaps sometimes, we'll want to behave differently so that we could explore or exploit more based on that. Okay, so as I explained before, policy optimization simply means that we're maximizing expected total reward. So we're now looking for a distribution. We're looking for a policy that will have a value that's greater than any other policy for every state and belief pair. And so to do this, what's convenient is to use what is known as Bellman's equation. And what this equation says is simply give you a recursive definition of the value. So the value, we said before that it was simply a sum of rewards, but that would be a possibly infinite sum. So perhaps what we can do is make that sum recursive, where we define the value at the current step as a sum of the current reward plus all the rewards in the future that are now captured by v, the value at the next step. Okay, so that's all there is to Bellman's equation. But the key now is that if we stick in here a max that says at each step we simply should take the action that will maximize this sum, then we'll have our optimal policy, right? Because this is, now you could work out an argument by induction that says, well, if you're optimal for the last step, and then you just ask for one step before, what should you do? Well, you should be optimal with respect to that step and the next one, and that will arise as a result of this max here. And then if you just do this all the time, then for every step you're always going to be optimal, and that gives you the optimal policy. Okay? So in a sense, Bellman's equation is what allows us to now have a policy that's going to be optimal in a non-myopic sense. Okay, so what's interesting is to compare Bellman's equation for classic reinforcement learning versus Bayesian reinforcement learning. And by classic, I simply mean when we try to come up with a policy that only depends on S as opposed to S and B. Right? So if we take B into account, then that means we're being Bayesian. And so it's the same equation, just that the arguments of S are slightly different. Right? But this is critical because here, if we're trying to come up with a best action, but we don't take into account what B is, what is our belief, then how can we optimize or trade-off between exploration and exploitation? We don't know what part of the model we know well and what part we don't know so well, so this won't work. At least we won't be able to come up with an optimal policy. So in practice, people usually use heuristics, and the popular ones would be Epson, Greedy, Boltzmann, etc. Okay. Whereas in Bayesian reinforcement learning, well, B tells us how much uncertainty we've got for different parts of the model, and this distribution here, the distribution over the next state, well, we can come up with its expectation simply by doing this integral here. So that gives us a model that's completely known. So we're back to, I guess, a Markov decision process here, and actually a partially observable Markov decision process. So before, you see, Bellman's equation, the problem is that we don't know this part, right? So that's by definition what we're missing for reinforcement learning. So we have to come up with heuristics for exploration, and then often, if we don't estimate that directly, then maybe through sampling we're going to introduce more approximation, and that works to some extent, but on the other hand, we won't be able to get something optimal. Whereas here, we know every part, and we also know what is our we know we can quantify what is our uncertainty about the model, and so that's how we're going to be able to get an optimal policy. Okay. All right, so let me walk you through now some algorithm as well as a parameterization for the value function, and then this will give us, I guess, a concrete way of optimizing policies. So how much time do I have left? 15 minutes? Okay, so yeah, I should have enough time. Okay, so now the tricky part of working with this form of Bellman's equation is that S here is discrete, B is continuous, and B is really Dirichlet, and I mean it's something that at least conceptually looks complex, right? So it's not clear that we can come up with a value function here that will be easily parameterizable. So the traditional way of dealing with this in reinforcement learning is you just use your favorite function approximator, like a neural network or a Gaussian process or anything, and then you just fit the value function. But what I'm going to show you is that the value function actually has a parametric form that's fairly simple. So we can actually work with the right thing from the outset. And so the key will be to show here that V is the upper envelope of a set of multivariate polynomials. So in other words, V is simply the max of some polynomial. And the proof of this is very simple. We can do it by induction. The way it works is that we're going to redefine V in terms of not the belief, but the underlying unknown model, theta, and then show that V of theta is really like this here, max of polynomials. And then we do this by induction by saying, okay, at the last step, we can have a polynomial that's trivial, just 0. Then, if we assume now by induction that the last step we've looked at, we've got a polynomial, or something that's max of a polynomial, then we can regress that through Bellman's equation by multiplying by theta, that's our unknown distribution, sum over S prime, add a constant that corresponds to the rewards, and all of this computation can be rewritten so that we've got one max at the beginning and then a polynomial after that. Okay, so in other words, value functions stay in the class of polynomials where we take a max over them. So this is great because now we'll have a way to represent and also approximate value functions in a more informed way than just using a neural network or anything else. Okay. So here's an algorithm that exploits this representation. There's a few caveats actually. Even though this is a neat representation, the problem is that now I should be able to come up with something like this for every belief, and I've got an infinite number of them. So a classic solution to this is simply to sample some belief points and then run Bellman's equation for each belief in my sample. Okay. So here, those 3 steps are simply Bellman's equation that I've rewritten in a more detailed fashion. That's usually how you would implement it in 3 steps in practice. And then we're going to essentially estimate what is the value at a bunch of belief points, and then come up with, I guess, a function over theta for each one of them, and then merge all of these functions into a set, and each one of them is really a polynomial. so that now when you put them all together, you simply need to look at the one that's at the top, so that's where the max comes in. Okay, so this is essentially just doing Bellman's equation on a bunch of belief points. Okay, another issue is that the number of polynomials, the number of monomials in each polynomial will grow exponentially with time. So even though we've got a nice parametric form, it's a form that isn't bounded in size, it grows over time. Okay, so a polynomial is simply a sum of monomials, and here the number of monomials grows by a factor of s at every step, and this arises from the summation that we've got here, this sum over s prime here. Okay, so this is going to be problematic. So here's a simple idea. Whenever we've got like mixtures of Gaussians, or in this case, they're really, I guess, linear combinations of monomials or Dirichlet, what you can do is always project onto a smaller number of components. So we can take our polynomial and approximate it by a linear combination of just a few monomials that we're going to treat as basis functions. So this way, at every step, if we project down like this, we're going to keep our representation bounded. Now, okay, how can we optimize for the coefficients here? So let's say that we've got basis functions already predefined, and we simply want to come up with the best coefficients. Well, we can solve an optimization problem that perhaps would minimize some ln norm. And if we use the Euclidean norm, it turns out that this optimization problem here can be done in closed form, and it's quite simple. So it simply solves a linear system, ax equals b, where a is this integral, b is this integral, and x is really the unknown that you're looking for. Okay? And so I guess what may be a little tricky when you look at this is all these integrals, but this arises from the fact that we're kind of doing, I guess, linear regression by minimizing Euclidean norm, but on functions instead of vectors. If I had vectors, right, I would simply be maximizing Euclidean norm, and then I would have a linear system like this, but I wouldn't have to talk about any integrals. The reason for these integrals is simply because I've got functions, but these integrals are easy to compute because these things are monomials, so the integral of a monomial is quite easy to do. Okay? All right, so if we employ this kind of projection scheme, then the next question is, where do the basis functions come from? And here we're going to use a trick that there's a similarity between how we do belief monitoring and how we compute the value function. So belief monitoring is this process where you start with a belief, get execute some action, get another state, and update that belief. Right? So it's a process that goes forward. Whereas when you do a Bellman backup, it's kind of going the other way around. You look at the last step, how much value you've got, and then based on the state you ended up in and the action that was executed, you can kind of regress and figure out what value you would have for one step to go. So it's the same thing, but in one case it's forward, in the other case it's backwards, and it turns out that the monomials for the beliefs tend to be the same as for the value function. And so we can do belief monitoring easily. We can figure out what those monomials are. So let's use them as basis functions for our value function. Okay. So to summarize, the algorithm would work as follows. There's two parts, an offline and online part. The offline is where you do the optimization of the policy, compute the value function. The online part is where you would learn by belief monitoring the transition model. And now what's a little confusing sometimes is that it looks like because we're doing the optimization of the policy offline that our policy is not going to adapt. But it does because the policy takes as input what the belief is here. So it's essentially a policy that would kind of capture all the possible situations, and then at runtime you simply tell, now you're in this situation or you're in that situation and so on, and therefore it adapts implicitly because of that. The caveat is that you have to essentially pre-compute what to do for every possible situation, and that's usually not possible, and therefore that's why we only pre-compute for a bunch of belief points, as I mentioned earlier, and this leads to an approximation. Okay. Okay, so the advantages of this approach is that it's going to be fast enough for online learning, and this was not always obvious before for model-based approaches because they construct a model and therefore it's more computation, and then people who do robotics, they'd like to be able to, I guess, select an action in real time, so a fraction of a second, and then we could do that here. And then the reason is because most of the computation is actually done offline. Okay, online there's not much to be done. Okay, the main disadvantage is that our policy is not going to be good everywhere, and that's simply because we're trying to pre-compute for every possible situations, which is not always realistic. Okay, so here are some experiments. We're going to compare this reinforcement learning strategy to two other strategies. Exploit is the classic myopic strategy that you would use in active learning. We're simply trying to be greedy and maximize expected value just for the current decision. Okay? So there's no notion of exploration here. The other possibility is that this Bellman equation, I didn't tell you this before, but it was really a partially observable Markov decision process because B, the belief, is really a distribution over some unknown, the model. So in a sense, you can view this as a partially observable Markov decision process, but it's a complicated one because it has continuous and discrete states. And then we don't have good algorithms for the continuous part, but we do have good algorithms for the discrete part, so let's just discretize the continuous part. The drawback is that discretizing anything continuous, it will grow exponentially with the dimensionality. Okay, so this doesn't scale well in practice, but it's a good test for comparison. Okay, and we tested this on some toy problems. So when I was telling you earlier that we're going to do some theory, so you see in this talk I showed you, I guess, how you can frame the problem, what would be the right way of I guess, dealing with the exploration exploitation trade-off and so on. But then computation, we're not at the point where this is going to scale a lot. Right? So here these are really just toy problems, just to show you, I guess, what's possible. And the first problem is a simple chain problem with just a few states. The more interesting one is here, hand washing. So this is a simplified version of what I mentioned earlier. Okay? And to judge the difficulty of the problem here, the column to look at is this one here about the number of free parameters. So usually people in reinforcement learning look at the number of states and actions to know how difficult the problem is, but that's actually the wrong way of looking at a problem. In machine learning, what makes a problem difficult is how many degrees of freedom you have, and that's really the number of free parameters, and it has nothing to do with the number of states or actions. Okay? So here you'll notice that 270 free parameters is actually a difficult problem, and even though it's a small state space. Okay? So it's all about how many free parameters your problem is going to have. Okay, and then, okay, BEETLE is here. This is Bayesian reinforcement learning. Opt is the optimal solution if you knew already all parts of your model. So this is really an upper bound that tells you how far we could be from optimal, but it's not clear that we can necessarily reach that value. Okay, and you'll notice that BEETLE does well on the problems that have just a few free parameters, but when the number of parameters grows, it's far from optimal, but on the other hand, it will do, I guess, better than the other techniques. Like this one here doesn't scale at all, so it runs out of memory. And this one here, it really depends if the problem requires exploration or not. It turns out that for the first one, there's actually no exploration needed, so it does extremely well. But on the second one, there is exploration needed, so it doesn't do so well. Okay? Okay, another interesting experiment is to see, since the learning problem is difficult when we've got lots of free parameters, now what if those free parameters we actually have prior knowledge about them? That could make the problem simpler. And in practice, if you know well your domain, you would not start with like something from scratch, right? You would know some information, and then you could start with a prior that's informative. So here, K is, as I explained before when I talked about Dirichlet, it's the parameter that tells us how peaked the distribution is. So as K increases, I've got more information, and therefore it's an easier learning problem. And what this shows is that the algorithm actually has better performance, as one would expect. Okay, so it generally increases with K. And then here are some learning curves that shows how well all these algorithms do on some of the harder problems. So hand washing tree, this was the hardest one. And then you can see that, I guess, with enough prior knowledge, so when K is equal to 30, right, then BEETLE does very well. But if it doesn't have enough prior knowledge, it's still far from optimal. And then exploit is lower. And then the other approach, the one that discretizes POMDP, doesn't even run here because it just doesn't scale. Okay, so to conclude, I guess the topic of this talk was to look at active learning, but in the cases where being non-myopic is critical. And then, and the reason for this is because at that point you've got an important exploration exploitation problem. And so what I tried to argue is that if we use Bayesian reinforcement learning, which is really like, I guess, something that may feel like is a more complex tool than you need for a lot of active learning problems, but in the case where really we've got an exploration exploitation trade-off, is really the right tool, then in that case, then we can really do this optimization optimally if we're being Bayesian. So that was the main thing here. And then the contributions, as I showed you, how you can parameterize a value function in a way that's exact, as opposed to just using your favorite function approximator without having a clue whether or not this is going to converge. Okay, and then there's an algorithm that exploits that. And okay, so for future work, well, okay, what I didn't talk about in this talk that I've already done is extend this to the partially observable case. So it turns out that all of this theory applies as well to the partially observable case. But then, okay, in the future, so we want to try this to learn user behaviors for assistive technologies, and then see as well how we could elicit information about users to set up the priors. In many situations, the transition models are also not stationary, so how can you extend this to dynamic systems? And then finally consider as well Dirichlets that would be correlated. So if you've got priors about two parameters, instead of just assuming that they're all independent, what if they're correlated? Okay, so maybe just one last slide about my research interest. So, okay, I talked a lot about Bayesian reinforcement learning and active learning, and I guess that's because I'm very interested in machine learning. Okay, so that fits right here, but in general, I'm interested in sequential decision making as well as semi-supervised learning. So these are, I guess, the main research areas, and then I get to apply this in health informatics. So currently I've got two projects beyond the one for hand washing where we're developing smart walkers, and another one about monitoring the symptoms of Alzheimer's disease. And then in another line of work, which is actually in collaboration with Google, we're looking at document clustering, and more specifically, how can we label the clusters? So I hope to give a talk on this, so otherwise maybe a Ting who's working with me on this could give a talk in the near future once we've got some good results about that, because this is some of the work that we're doing in collaboration with Google. Okay.
Okay. So any questions?
So I have in mind a problem where if I want to do the cost on every input is computational time, okay? To get which label it is, it takes a lot of time to get. How much reward do I get by trying to how much faster will I be by using your strategies rather than just spending a lot of time computing every input and do my classification with standard algorithms?
Right. Okay, so when the reward is in terms of computation time, so this is a very interesting problem that's known as doing bounded reasoning.
Okay.
Okay. And there's been some work, actually, people have used reinforcement learning to look at this, where the idea is that you can gather some statistics about how much time it would take to compute different things, and then run a reinforcement learning algorithm on top of that to optimize and decide at any point in time which thing you should be computing that will, be short and perhaps give you the most information. So here I'm really talking about reinforcement learning on top as a meta-learning problem or meta-learning algorithm, right? And then keeping all of your options open at the lower level and gathering some statistics about them. So that's one way people have approached this, and yeah, the literature is bounded reasoning.
Okay, thanks.
Any other questions? Okay, I also have a question. So,
Good.
So this isn't super related to your talk, or if it is, I missed the connection. But the last time I built a linear classifier, which wasn't actually at Google, one of the things that we did, which I don't really know if it's standard practice, is we introduced random dimension to try to make sure that the output was reasonable. That if the random dimension attracted a non-zero coefficient, that probably indicated a problem. I'm just wondering, is that sort of standard practice in machine learning circles? And if it is, how does that affect sort of your approach here in terms of trying to optimize the sequence of choices?
Okay, I'm not sure I'm totally understanding the question. So you've got a problem. You're adding random dimensions to it.
Just one random dimension.
One random dimension. And then what's the purpose of adding this?
So
Again?
at the end of the day, with linear classification, you get a set of coefficients that divide your points, right?
Right.
And so the coefficient on the random dimension ought to be 0 because it's not informative. If it's not close to 0, then you might worry that you haven't really done a valid classification because apparently the random signal is strong, and that would be an indication that the whole thing did not work the way you expected it to.
So okay, by adding this this additional dimension where everything is random, you're essentially verifying that your algorithm is not overfitting. Is that what's going on here?
Sure, yeah. You're essentially verifying that the labeling that you fed into the linear classifier caused you to do a true classification as opposed to pick up on random noise.
Right. Okay.
Right.
Yeah, so you could think of this as an alternative to, let's say, cross-validation or other techniques to ensure that you're not overfitting. Now, okay, I think I understand the question, but or at least the setting. But you wanted to know if it would make sense for me to do this in my setting as well?
No, so I guess that you've indirectly answered my first question, which is I just didn't know if this was a standard practice in machine learning circles. Sounds like it's not.
Practice, yes. I've never seen this, but then it seems like a good idea. In my mind, I would think of it really as just another approach for verifying that your classifier is not overfitting.
Right.
Yeah.
So then I was wondering if it had been a standard practice, which it's not, whether it affects your approaches for optimizing the sequence. But since you've not tried it, then you wouldn't know for sure whether it would make a difference.
No, I haven't tried it. So here, so in reinforcement learning, I guess, in any types of machine learning, I guess overfitting is definitely a possibility. But, okay, I'm using a Bayesian approach where I guess the key is how I define the prior. So normally, one way of dealing with overfitting in machine learning is that you define a prior that will penalize the more complex hypotheses, so that perhaps you're only going to use these if they're really going to help, and if they're only going to capture, I guess, random noise, which you don't want, then the penalty will essentially help you to rule them out. Okay, so and a lot of machine learning approaches, then people would either use a notion of a penalty or a prior that implicitly puts penalties on the more complex functions to regulate and deal with overfitting in this way. So in my case, that's how I'm dealing with that problem. That being said, there's probably a way to use the idea that you just suggested, and it would be very interesting to see how, I guess, how well it will work and so on. Yeah.
Okay, thanks.
What was the gamma in Bellman's equation?
Oh, gamma is the discount factor, right? I didn't mention it. The idea is that you would normally maximize the sum of rewards, but depending on the setting, you may decide that you want to discount as if there was some kind of inflation rate the future rewards. And you would usually take it to be smaller than 1 and non-zero.
So for your algorithm, or even for reinforcement learning problem, I'm assuming that machines and time wouldn't really be a constraint, machine power and times wouldn't really be a constraint. Is your algorithm or the other algorithms really bound to the number of features that they can actually handle for learning?
Okay,
maybe
so
they don't scale
time
over.
And space is not a constraint. That's a good question. Well, so in some sense, I guess if time and space is not a constraint, I mean, we've got Bellman's equation, and then we know that the optimal policy satisfies Bellman's equation, so it's just a matter of finding something that satisfies it, and then you could use your favorite search technique for that, or, I mean, I guess, yeah, we could do Bayesian reinforcement learning perfectly in that sense. Yeah. But then, on the other hand, I mean, that's more or less what the guys in operations research were advocating at the beginning. In the 1960s, they laid out all the equations, but they just didn't have the computational tools, so that didn't really go anywhere. And then it's today that now we're looking at this work again, and then going back to, I guess, those equations that were quite elegant and giving us exactly what we want, but then finding out ways of dealing with the computational complexity. So I'm not sure that, well, I think there's a lot of problems out there that if space and time was not an issue, we already have the solution. It's when you include those two constraints that all the problems arise.
Just know that in some algorithms are not able to converge or reach any good learning point. If you increase the dimensionality or the number of features, it's just not able to handle.
Oh, okay, right. So I guess, yeah, here your question was, how does this varies with dimensionality and so on? Well, so in this problem, I guess, yeah, I didn't talk about the computational complexity, but so okay, here I was assuming I've got a discrete state space, and then I could think of features as being discrete variables that have a certain number of values each, right? And then if I increase my number of features, usually it increases my state space in an exponential fashion, right? But then if I don't care about time or space, it doesn't matter. So I would argue here that the math will work out. It's only in the limit if you deal with infinite spaces that things would be a bit more tricky. But otherwise, if you're still working in finite spaces, I would argue here that there's no issue.
All right, thank you.
Yeah.
Okay, let's thank the speaker if nobody else has any questions.
I just have one more question. What looks suspicious a little bit that even if we're completely wrong in our assumptions about prior beliefs, we're still better than exploit algorithm. Is it true? Like, according to a graph, we're still better.
Oh, okay. So here, I guess I made the right assumption. I set up the prior in a way that it's a good prior.
No, like you showed two cases with bad prior and a good prior, as I understood, like yellow, red and green lines.
It's more as an informative prior versus an uninformative prior. So both of them are good priors in the sense that they, well, okay, so let's go back to, I have this graph. Yeah, so it would be kind of like looking at this red curve and the green curve, right? Let's say that the true model is at point 2 here, right? Both of them are kind of good in the sense that they have the peak at the right location. It's just that one is way more informative because the peak is much more higher. It's much higher at point 2, right? And so I guess in what I showed, so with k equals 0 and k equals 30, so k equals 0 would actually correspond to the blue line, so it's completely uninformative, so you start with a uniform distribution, and k equals 30 would be kind of like, I guess here, maybe the red line, right? So we already are pretty certain about where the true model is. What would be interesting is to see now if I didn't have the peak at the right location, right? So if I had an informative prior that's wrong, right, then it could hurt me in the sense that it would take more time, and then in the limit, I guess if my prior probability of the true model is 0, then I'll obviously never converge, right? So I have to have a non-zero probability for the true model.
Okay.
Okay, thank you.
Thank you. Okay.